So today we are going to resume our discussion from the exercises in chapter 4, the floating car data chapter. We have two sections, traffic state estimation using floating car data and analysis of extended floating car data. Once we are done with these two, we are going to start the next chapter, which is about cross-sectional data. We'll not cover a lot of it today, but we'll get to complete some of the introduction. And then we are also going to start adding equations from this book to our Python package. Can everyone see my screen? Any problems viewing it?
Everything is good.
Okay, thank you. Let's go back. So let's start with traffic state estimation using floating car data. Let's read the question. It says, consider a motorway with 4 lanes per driving direction, where traffic flows with 1500 vehicle per hour per lane and density is 20 vehicles per kilometer and lane, into a region of congestion where density changes to 75 vehicles per kilometer per lane. Assume a probe vehicle percentage of 1%, providing their location data to a traffic data center. Let's try to solve the first part of the question, which is asking for determining the partial density of equipped vehicles for all 4 lanes upstream of and within the jammed region. So just to review, floating cars are limited number of vehicles which have the sensors or using smartphones to collect data out of the total traffic. So the probe vehicle percentage that is given to us is represented as theta in this chapter. So let's highlight that. So this is the probe vehicle percentage of 1%, and this is theta. This is our theta. And what we want to do is we want to estimate partial density of these floating cars because we only have a limited number of floating cars. So determine the partial density of these equipped vehicles over all 4 lanes upstream of and within the jammed region. So the jammed region is this one, where the density changes to 75, and the upstream is the density of 20 vehicles per kilometer. The flow remains the same as 1500 vehicles per hour per lane. So if we have the density given to us for the uncongested region, which is 20, and we also know that only 1% of those vehicles are floating cars, we just simply need to estimate that 1% of 20 vehicles per kilometer per lane. So that will be 20 divided by 100. That will give us a partial density in uncongested region. Similarly, for 75 vehicles per kilometer per lane, it would be 75 divided by 100 because we are multiplying it with 1%. That will give us a partial density. So let's see what the solution says. I believe it is 678. No, 677. So here is the solution for the first one. It says with a penetration level of 1% of floating cars, the partial density over all 4 lanes as a function of the 1 lane density rho is given by the theta into the actual density, and we also multiply it with 4. So when we do that for uncongested region, we have 20 divided by 100 into 4. That comes out to be 0.8. Just to confirm that, here's 20 divided by 100 multiplied with 4, and we get 0.8. And the same thing for the density of 75. So we have 75 divided by 100 into 4. That gives us 3 vehicles per kilometer. So this is the partial density from floating car data. Any questions? Hmm. Something's wrong with the page number. Okay. Next is assume that the congested region extends over 4 kilometers. How many probe cars are on average inside this region? So we know that the flow is 1500 vehicles per hour per lane. And here the assumption is that instead of just 1 kilometer, we now have this flow over 4 kilometer. How many probe cars are on average inside this region? So we want to find the number of vehicles in this region. So if we consider the flow of 1500 vehicles per hour per lane and we multiply it with 4, that comes out to be 6,000. So we have 6,000 vehicles per hour per 4 kilometer. And we want to find the number of probe cars. What we do is we know that there are only 1% of floating cars there. So we just get 1% of 6,000. So that should give us 60 vehicles. Let's see. So here we have number 2. Nope, I was wrong. So number 2, it says on average there are 4 kilometers into 3 vehicles per kilometer. Yeah, because the flow doesn't change with the kilometer. The flow is fixed for a given lane. So wherever we have estimated the flow, because it is generally estimated at a fixed location, that's where we get that. So the flow is not a spatial quantity, it is temporal quantity. So I was definitely wrong there. So what they've done is they've taken the 3 vehicles per kilometer density, the partial density of the vehicles, and then multiplied it with 4. That gives us 12 vehicles inside this congested region. That makes sense because initially we were only looking at 1 kilometer. Now we were told that there are 4, so we just multiply that. Doesn't like any page numbers I'm giving it. Right. Number 3 is assume that the traffic jam fronts are nearly stationary and the probe vehicles report when they are entering and leaving the traffic jam. Furthermore, the average speed of floating cars is the same as that of all vehicles. Determine the average update frequency for the jam front positions and the segment travel times. So this question is a mouthful. Let's look at it again. Assume that the traffic jam fronts are nearly stationary. The word stationary here is, I think, statistical stationary, which the chapter has previously mentioned, I think. If not, it is mentioned in the next chapter. And stationary or statistically stationary means that the distribution of the variable we are interested in is not changing. So if the distribution is represented by a normal distribution, then we have two parameters of mean and standard deviation. So those do not change as we look at the variable over time. So if we are looking at speed, for example, the speeds don't change over time. So here they say that traffic jam fronts are nearly stationary, which means that the congestion that we are observing is not changing, it's the same over time. And the probe vehicles report when they are entering and leaving the traffic jam. So the vehicles enter and leave the traffic jam and they only report it then. Furthermore, the average speed of the floating cars is the same as that of all vehicles. So another piece of information that we are getting here is that no difference in speed is observed between floating cars and the other vehicles. Determine the average update frequency for the jam front positions and the segment travel times. This question is actually asking us how often are we updated uh, by the floating car data? How often are we getting that floating car data? Is it happening every 30 seconds? Is it happening every minute or 15 minutes? That's what the question is. So let's see what the solution says here. So here's number 3. If the traffic jam fronts are stationary, the flow through the jam fronts free to congested and congested to free. This is what the term jam front means. That you are going from free traffic to congested traffic and then from congested traffic to free traffic. The flow is going to be 6,000 vehicles per hour. So we were initially told that the flow was 1,500 vehicles per hour. But now we are multiplying that number with 4. So the question is, where is that coming from? Why is the total flow now 6,000 vehicles per hour? I think that is because there are 4 lanes. We were told that the flow in the question was 1,500 vehicles per hour per lane. So this is the total flow. If furthermore, the average speed of the floating cars is the same as that of all vehicles, the partial flow is given by, again, it's 1% of the total flow, which is given to us in the question. The penetration rate was 1%. So we take 6,000, we multiply that with 0.01, and we get 60 vehicles per hour. So we have an average rate of 1 update of the jam front positions and the segment travel time per minute. We conclude that even for a very small penetration level of 1%, we have a sufficient update rate. Since 1 hour has 60 minutes and we are getting 60 vehicles per hour, that means, as the question told us, that the floating cars are reporting when they are entering the traffic jam front and when they're exiting. So that means we are getting information from those vehicles every minute, as also explained in the answer here. Which also tells us that even though there are only 1% of the vehicles who are probe vehicles or floating cars, we still are getting updates every minute. So it is still very useful. Okay, questions? Any comments? All right. Next section is about analysis of extended floating car data. And just to review, extended floating car data is where we have extra information other than the time positions, and the positions are the geographic positions. So we have timestamp and geographic positions. This is the normal minimal floating car data. Extended floating car data will get pedal positions and other types of information, for example, acceleration and so on. Consider the platoon of 4 floating cars whose data are displayed in figure 4.11. Let's look at that. So here is 4 floating cars. We have vehicle 1, which is represented by black line, and then we have 3 more vehicles, which are the followers. And we also see, so the top plot here is the speed over time, and the bottom plot is the bumper to bumper gap over time. So we have vehicle 1 to 2, 2 to 3, 3 to 4. We can observe those gaps. So we already see that there's some difference in the gaps. Even though speeds look more or less the same, there is some lag, but there is some difference in the gaps of the vehicles. So what does the question say? Discuss qualitatively whether the car following dynamics shows flow instabilities by looking at the oscillations of the 3 followers. So we need to qualitatively discuss if there is flow instability by looking at the oscillation of the 3 followers. So let's look at this again. So by oscillation, I think it means that do we observe speeds increasing and decreasing? We observe that significantly in this region where vehicle increase speed, decrease speed, increase again, and decrease again. So I think these are the oscillations which is happening after about 225 seconds. So we do observe that. So there does seem to be some flow instability. But in traffic engineering, stability has a particular definition, and there are two types of stabilities. There's local stability and string stability. And we have not yet discussed that, but the book will explain that to us in the later chapters. I believe it's chapter 16. But it does seem that there's some instability, but we cannot quantify that as we do not have the relevant tools right now. So let's see what the answer says here. Here, the episode time greater than 225 seconds is most revealing since the leader already shows oscillations, while the speed amplitude from the local minimum to the local maximum of the leader is on average about 3 meters per second. That of the follower increases to about 5 meters per second for the last follower. Here, hence, this is the evidence, or there is evidence for flow instabilities. More precisely, the following behavior is locally stable, but string unstable, as described later in chapter 16. We can confirm what is mentioned here about the oscillation of the leader and the last follower. Let's do that. So here in the figure, you can see that this is the maxima, for example, this is the maxima of the leader. If you look at this time, this would be around 236 or 37. And the minima only in this region is this one. So it is about 234. So 237 minus 234 would be 3 meters per second, as the answer says there. The last follower here is vehicle number 4 with blue dot dash line. And the maxima for that is 245 seconds. And the minima is about 230 seconds. So that would mean, sorry, 235 seconds. That seems to be like 10 seconds, not 5 seconds of difference. Oh, sorry, we are not looking at time, we are looking at speed. So this here, this is just close to this tick mark, which is 10 meters per second over there. And this here, the lowest is here. So yeah, the difference between them is 5 meters per second. And if you look at this maxima, this is also very close to 10. So I would consider this as 10. And this one here is definitely above 5. So the difference does seem to be 3 meters per second. Yeah, so there is difference between the oscillations of the leader and the oscillations of the last follower. And according to the answer, it is indicating string instability, but local stability. And we'll get to chapter 16 to figure out what that means. Any questions? Okay, next, number 2, estimate the average delay in the speed responses. So how do we estimate the average delay? So for example, if you take this point, let me actually go to this location and then actually take the screenshot of these figures. And let's try to annotate the times when we see the same behavior. So here we are, and if I take this line and let's use the red color here. So here we have the time when it has the maxima in this congested region. And then the first follower is vehicle number 2. So here we have this as the time. So this is about 230 seconds, and this one is probably 228 seconds. So this seems to be like 1.5 to 2 seconds of lag. Now, the third one is here. Let's take this again. Third one is here. And let me draw that one again. So it does seem that the difference in time between these points where we have the exact same behavior of the maximum speed, this seems to be similar, and this seems to be between 1.5 and 2 seconds long. So that's what the question was asking. Let's see what they say there. The maxima and minima of excuse me of the speed curves of the leader and the last follower are shifted by about 5 seconds. So they've looked at the leader and the last follower. Thus, the average delay in the individual follower's response is the order of 1.5 to 2 seconds. So I have not looked at the last follower. I've only looked at the consecutive followers, the consecutive pairs, and there we see that's about 1.5 to 2 seconds. There's also a footnote here. This is not necessarily due to reaction times. In chapter 11 and 12, we will see that even models with zero reaction times display such a delay. This is very interesting because on the surface, it does seem that the reason why we see the same behavior of the followers after some time lag is because of the reaction time. But according to the authors, that's not necessarily the case. There may be other things happening even for those car following models that produce trajectories where still we observe this lag. So we'll find out what that means when we get to those chapters. Okay. Then next is number 3, estimate the maximum accelerations and braking decelerations. For acceleration and deceleration, we need to look at the max as the question asks. And so we see this slope seems to be the maximum when we look at all the speed decreases, and this slope seems to be the maximum when we see all the increases. And to estimate acceleration and deceleration, we know on y-axis we have speed, on x-axis we have time, so the slope will give us the acceleration. So if we, for example, take this as one point and another point here, and then take the slope of these 2 points, let's try doing that. So here we have this time, and then again, we have this time. So we need to find these times. So this, the 215 seems to be somewhere here. This may be 212. And this may be 220, sorry, 217. So this may be 5 seconds. And we also need the speed there. So this is, let's try to draw a horizontal line here, just above 10. And if we do the same thing here, okay. So here we see this may be 11, and this may be 1. So difference between them is 10 seconds, and this is, sorry, 10 meters per second, and this is 5 seconds. So once we have 10 divided by 5, we get 2. This seems to be the acceleration, sorry, deceleration. And this slope, at least the part until here, does seem to be the same as that, maybe a bit more higher slope than this one, but apparently they look similar. So I would say acceleration is also the same magnitude as deceleration. Let's see what the answer says. This is number 3. So here it says between time 214 and 218 seconds, the speed drops from about 11 meters per second to 1 meters per second. Oh, I was correct. Corresponding to a maximum deceleration of 2.5 meters per second squared. Okay, so instead of 5 seconds, sorry, they found 4 seconds. In my estimation, it was 217 and 212, but in their estimation, it was 218 and 214 times. And so we get a deceleration of 2.5, and the maximum acceleration has the same order. So they have an estimate of 2.5 for both acceleration and deceleration. Final question, floating car data. Is it possible to discern different driving styles of the 3 followers? Consider the episode time less than or equal to 200 seconds of nearly constant speed following to determine the average car following time gaps, and the episode where the vehicles stop to determine minimum gaps. Okay, so time less than 200 seconds is going to be, let me first remove these annotations. So we are looking at time less than or equal to 200 seconds, so just below this time. So we see here the speeds are, they're not oscillating, there's some variation in the speeds, but they look more or less the same. They are around the speed of the leader. But within the same time, we see that there are different gaps. For example, vehicle one is, sorry, vehicle number 2 is following vehicle number 1, and that is represented by this line. So this line has a higher gap definitely than the vehicle 4 that is following vehicle 3. Similarly, vehicle 3, sorry, vehicle 2, no, vehicle 3 that is following vehicle 2 is also having a small gap compared to vehicle 2. So we see that there definitely is a different driving style here because they are keeping the same speed or similar speeds, but different gaps. So I would say yes, there is definitely different driving style that we can observe here. And then the question also mentions this part where we have vehicles stopped. So when the vehicles were stopped, we see that uh, the gaps are again different, at least for vehicle 2 compared to other vehicles. So yes, there is definitely different driving styles in play here. Let's see the answer. The last driver, vehicle 4, follows most closely with time gaps SI divided by VI, strongly varying but generally below 1 second. SI, just review, is the distance headway, and VI is the speed. It says that this ratio or the time gap is generally below 1 second, and it's talking about this thing. this part where we have the smallest gap. So bumper to bumper gap here. This is, I think this is SI minus the length of the vehicle. The shortest minimum gap, about 1 meters, however, is observed for the driver of vehicle number 3. Shortest minimum gap. Shortest minimum gap is right here. So this is definitely vehicle 3 following vehicle number 2. And that happens when they are stopped. Any questions, anything you want to add here before we switch to the next chapter? All right, let's start our next chapter. So far, we have discussed trajectory data, floating car data, and now we are looking at another source of data in traffic engineering, which is called as cross-sectional data. So cross-sectional data is where we have different ways to measure or get data at a cross-section of a road. This is shown here, where this vehicle is arriving, and this is a loop detector, which is embedded in the road. And as the vehicle enters this, the front of the vehicle enters the loop, we see the voltage starts to decrease. The time that happens, we call that as TI0. I represents the vehicle number, and 0 means that this is the front of the vehicle that has entered the loop. And when the rear of the vehicle leaves the loop, then is time TI1, and that's where the voltage would start to increase again. And so the difference between these times tells us that there was a vehicle on the loop for that amount of time. So there are not only these induction loops that are embedded in the road, but there are also other ways to measure cross-sectional data. So we have a road, and there's a fixed cross section where we can either put pneumatic tubes. We can also use a radar or infrared sensors or light barriers, which are relatively low cost solutions compared to induction loops, which need to be embedded in the road. So we've already talked about the times when the front of the vehicle enters the loop and times when they leave. There's also in this figure 5.2, I have highlighted it here in this part where we have the loops shown here, and these are two loops, not just a single loop, but two loops, one after the other. And the distance between them is typically 2 meters, as mentioned in the chapter. It does mention here that it is impossible for single loop detectors to measure vehicle speed, and this is where we need to get two loops, so double loop detectors. And as I mentioned before, the typical distance between them could be 2 meters, it could be others as well, but the chapter only mentions 2 meters. So we get some of the quantities directly from the loops, but we can also get the secondary microscopic quantities. These are actually the directly measured quantities. The length of the vehicle can be measured because we are looking at TI1, which is the time when the rear of the vehicle has left the loop, and TI0 when the vehicle entered the front of the vehicle entered the loop. So this tells us how long the vehicle was detected, multiplied with the vehicle speed. That will give us the length of the vehicle, because the distance that this vehicle has covered while it was inside the loop is the length. We also can determine vehicle type by classifying the length Li. We can also get directly the time headway, and time headway is the time difference between a vehicle entering the loop and then the following vehicle entering the same loop. And that is the reason why we are using TI0 in both cases. So 0 indicates when the front of the vehicle has entered. So we are now looking at I minus 1. I minus 1 means the lead vehicle. So the lead vehicle has entered. If I draw this here, so we have this road segment and we have this on this cross section we have the loop detector. So the first vehicle has its front center entering the loop and then it leaves. Then whatever is the second vehicle, the follower to this vehicle, it also enters and then we determine that using TI0. So TI minus 1 and superscript 0 will give us when the front of the leader enters the loop, and TI0 will give us when the front of the follower enters the loop. The difference between them will give us time headway. There's also a time gap, and actually what I've drawn there is also shown here. So in figure 5.3, we have single vehicle data as measured by an induction loop or any other cross-sectional detector. The shaded area indicates the detector occupancy at different times. We'll see occupancy in a moment. So just like the time headway, as we discussed above, there's also time gap. So instead of Ti minus 1 superscript 0, if we use Ti minus 1 superscript 1, which is when the rear of the vehicle has left the loop, and this is the leader, if we take that time and subtract it from the time when the front of the follower entered the loop, we'll get the capital Ti, which is a time gap. It is also equivalent to whatever is the time headway, delta Ti, minus the speed of the leader divided by the length of the leader. Then we can also get distance headway. All of these quantities are directly measured by this cross-sectional data, by the loop detector. So distance headway is Di equals the speed of the leader into the time headway. And then the distance gap is we take the distance headway and subtract the leader's length. That will give us distance gap. So all of these quantities can be directly estimated, actually not estimated, directly given to us by these detectors. We can also then aggregate all of this data. And typically, according to the chapter, what happens is that there's a fixed time interval, delta t, which could be, for example, 30 seconds, 60 seconds, 2 minutes. And for that fixed time interval, it would aggregate all of this data, the microscopic data that we have discussed here, and then send that to the traffic control center instead of the microscopic data, which means that we lose this very valuable information that we can potentially get every time a vehicle enters the loop. And that is because to save the bandwidths and the disk space. I'm pretty sure that modern systems do provide microscopic data because now there's more capability of storing all of this data by compressing it. So the macroscopic data or aggregated data is done for delta t of 20 seconds to 5 minutes. And just to be clear, delta t here is the aggregation time interval, which is different from delta ti here, which is the time headway. So please don't confuse these two. So it also mentions here that we can, yes, look at delta t of, for example, 60 seconds, and then we get what is the average speed. So we have Vi of all the vehicles which were observed by the detector within 1 minute. So we take all those vehicles, take an average of that, for example, a time mean speed, and that gives that is given to the traffic control center as aggregated data. So that is the time aggregation. But we can also have aggregation by the number of vehicles. So instead of time aggregation, we are now looking at 50 vehicles. So every time 50 vehicles are detected by the detector, it will then aggregate the data and then send that to the traffic control center. So that is the second option, which according to the chapter is more meaningful statistically. And there's a question later where we will discuss this, why that is the case. Um, any questions? Anything you want to add here? So now traffic flow can be directly given to us by the detector data, which we know is equal to the number of vehicles passing that cross section at whatever location that cross section is, divided by the aggregation time interval, which is delta t. It is also equal to 1 divided by the average of the time headways. So we observe multiple vehicles and we observe their time headways. We have already discussed what time headways are. If we take the expected value of those time headways, and by expected value we mean the average of the time headways, and then we take a reciprocal of that, that will also give us the traffic flow. And so here now they define a new thing for us, which is microscopic flow, which is that if the traffic flow is equivalent to the reciprocal of average of the time headways, then an individual time headway is also correlated to an individual flow, which they term as microscopic flow. So Qi, microscopic flow, is equal to 1 divided by the time headway. And here I represents a vehicle. So Q1, for example, is for vehicle number 1. And we know that vehicle number 1 has a leader, vehicle number 1 minus 1, which is 0. So it has a headway, a time headway from that vehicle, which is given by delta Ti. So if we take 1 divided by that time headway, that will give us microscopic flow. And then it mentions here that scatter plot of this microscopic flow versus speed will give us the microscopic flow density diagram. I think this is a typo. It should not say microscopic flow density diagram because we do have flow, but this is speed, this is not density. It should instead say microscopic fundamental diagram because here in the footnote it mentions, notice that the term microscopic fundamental diagram generally denotes the gap as a function of the speed for steady state traffic flow as given by microscopic models. So whenever we get to the microscopic models, we'll better understand what this footnote means. But right now, I want to indicate that this is a typo. This should say microscopic fundamental diagram. Because in the fundamental diagram, which this chapter covers later, we are not going to cover that today, but fundamental diagram has 3 different scatter plots. One of them is flow density, but there's another one which is flow speed. So microscopic fundamental diagram will also include flow and speed, but this is just a type. We emphasize that the traffic flow Q can be considered as the harmonic mean of the microscopic flow. So here they also show in equation 5.8 the relationship between the traffic flow and the microscopic flow by simply reusing this equation and replacing delta Ti with 1 over Qi from equation 5.7. So that gives us the relationship between traffic flow and the microscopic flow. The next thing is occupancy. So The detector data is sending the traffic flow to the traffic control center. It is also sending the occupancy. So what is occupancy? Occupancy does not have any units, so that's why it says here that it's dimensionless. It is a fraction of the aggregation interval during which the cross section is occupied by a vehicle. Our aggregation interval is delta t. So this is delta t. For example, 60 seconds. So within that minute, we observe for vehicle I when it entered the loop and when it left the loop. Subtracting these times gives us the total time that the vehicle was observed by the detector. And when we do that for all vehicles I, from I is equal to 0 to whatever is delta n minus 1, that will give us the complete time, all of the time that the vehicles were observed. Let's say there are 15 vehicles that were observed, and we observed their time to enter and leave the loop. We sum all of that, which gives us this thing, and then we divide it by the total aggregation time interval, which will give us the fraction of the aggregation interval during which the vehicles were occupying the cross section. So that is occupancy. If the occupancy is higher, then that means there were a lot more vehicles there observed by the detector. If the occupancy is smaller, then that's the opposite of smaller number of vehicles. So the detector data also gets arithmetic mean speed and send it to traffic control center. Similarly, harmonic mean speed and the arithmetic time mean of microscopic flow as well as speed variance. But it mentions here that other than the traffic flow, occupancy, and arithmetic mean speed, these variables may not be sent. So not all vendors send this information to the traffic control center, but some do. So arithmetic mean speed is simply the average of the individual vehicle speeds that the detector is observing. That's why we take the sum of all the vehicle speeds divided by the total number of vehicles. And here it says to emphasize that the speed is measured at a fixed location for a time interval. V is sometimes called time mean speed. We also know from previous discussions that there's also something called as harmonic mean speed, which sometimes represents space mean speed. And that is when we take the harmonic average. So we take the number of vehicles in the numerator and the reciprocal of the individual speeds in the denominator here, and we sum all of those. That will give us harmonic mean speed. We have already discussed the microscopic flow. We can then aggregate that as well by taking the expected value or average of the microscopic flow. So we have multiple vehicles I, and for each of them we find the microscopic flow, which is equal to 1 divided by the time headway. And then we take the average of that. That will give us Q star, which is the aggregated microscopic flow. So remember, the aggregated microscopic flow is not equal to traffic flow. It is equal to arithmetic time mean of microscopic flow. So these are different things. That's why this is Q star, and the original quantity that we have discussed so far, that is traffic flow Q. Here it says, unfortunately, Q star is rarely given, but it is very useful in estimating the density when no microscopic data are available, which is typically the case when these data are sent to traffic control center. Finally, there's also speed variance. Variance is the statistical concept. Standard deviation is easier to understand, in my opinion, where standard deviation is the, on average, how much variation we are observing in a variable. For example, speed. So how much are the speeds varying compared to the mean speed? That's what the standard deviation is. We can also determine coefficient of variation, which is the standard deviation in speed divided by the average speed, and here they're using time mean speed. So that also quantifies the relative spread of the speed values. And now the final thing before we wrap up this section of our discussion is this question: considering the mean speed in a highly heterogeneous traffic flow. So heterogeneous traffic flow means it's not homogeneous. Some speeds are higher, others are smaller, but we are looking at the mean speed. What is the advantage of averaging over a fixed number of vehicles instead of over fixed time intervals? So far, we have discussed that detector data will aggregate the variables for delta t and then send that to the traffic control center. Here, the question is asking, what is the advantage of not doing that, but instead averaging for every n number of vehicles, for example, every 50 number of vehicles. So, what do you think is the advantage of using n number of the average on over n number of vehicles instead of delta t? Any ideas? So with delta t, the possible issue could be that for if we are doing, for example, for 30 seconds, in the first 30 seconds of our observation, maybe there were 10 vehicles that were observed. In the next 30 seconds, there were five. So the number of vehicles are not going to be necessarily the same in our aggregation time interval. And so sometimes there may be no vehicle at all observed, right? So there could be missing data. There could also be misrepresented data because sometimes there are more vehicles observed, sometimes less. If we know that we are aggregating over a fixed number of vehicles, then we know, okay, we observed these first 50 vehicles, and this is the average speed, this is the flow, and so on. Now we observe the next 50 vehicles. So every time we are comparing apple to apple, I think it makes more sense to compare a fixed number of vehicles or aggregation over a fixed number of vehicles rather than time interval. Okay, so we are done with our discussion of the book chapter. We are now going to add equations to our Python package. So I'm going to switch to positron. I'm using positron IDE for developing the package. Positron IDE, by the way, is very similar to VS Code because it is based on the same uh, bare bones IDE that Microsoft uses to develop VS Code, but it is made particularly for Python and R users because it provides us this console right away. In VS Code, you need to uh, get your terminal to show you the console, but Positron IDE has this built in, and it does the same thing for our programming language as well. So that's why I'm going to use this. In the last discussion we had, while we were developing this package, I ran this command uv init dash dash lib and then the name of the package. So this is the name that I wanted, traffic flow dynamics, because we are developing the package for the book. UV is a Python package manager and project manager, which is pretty new and it is very fast. So we are using this. You need to install it by going to UV website and install it for your system. Init will initialize a new project. But when we use these flags, dash dash lib, when we use this flag of lib, it means that we are developing a package, not just any Python project. We are actually making a Python package. And then we provide the name. So after running that, it created this folder, which we are now in. And then within this folder, you can see it here, the name TFD. Within the folder, it created the src folder, and it also created gitignore file, Python version, pyproject.toml file, and readme. So let's start looking at these files. Readme.md is currently empty. This is what I provide, and I need to fill it out to provide information about what this package does. PyProject.toml is what the package created for me. And this is where it will keep track of all the dependencies, all the packages, Python packages that I'm going to use for my purpose. And it also provides some metadata about the package. So for example, the name of the package, the version, the description. So here I put collection of equations and scenario details from the book Traffic Flow Dynamics second edition. But this could be anything that you'd like to add. Then authors, I added TSLC as the author and I added my email here. And then it requires Python more than 3.11. So at least 3.11 version of Python is needed. Otherwise, the package is not going to work. Currently, there are no dependencies because we didn't add anything. And then this is something that is automatically generated by UB, which is the build system, which means how are my package files going to be built to make it a package. Python version is also added by uh, positron, which in this case, since my highest version of Python available on my system is 3.14, it used that by default. But if I want, I can change it. Then gitignore is adding some of the things here already, which means that ignore the files when I'm putting this in version control, when I'm putting it on GitHub. So it will ignore some of these files. For example, you see dist and venv. Um, these two appeared after I did something, which I will show you in a moment, but they don't appear when you first create the package. But we don't want to put this in our version control because this is something that whoever is installing your package would build when they install it. So we don't want to do that. That's why this is added in gitignore so that whenever we put everything on GitHub, it does not, this folder does not go with it. Similarly, venv is a virtual environment, and we are creating it because we want to add everything um, that we are using, all the dependencies in this environment, and we don't want to actually touch our main Python installation. We want to keep it clear from this project because we may have another project, another package that we are developing, or something else that we are doing in Python where we are using some other packages or some other versions of the same packages we are using here. So we don't want to conflict with that. So we create a virtual environment which will contain all the packages that we are using only in this project. And then you also see this rough cache, which is just for linting or just checking if there are any problems with my files, any conventions that I am not following, etc. So, but this only happens once you run a command because I've already ran that before. This and that showed up. By default, nothing of these three files or folders would show up when you first create the UV package. SRC folder contains another folder called TFD. So TFD is the main folder. Within TFD, we have SRC, which means source. And then within source, we have another folder called as TFD again. And this is the source folder. This is where all the files for your package will go. Any functionality that you want to add will go here. And by default, what it adds is this thing. It's just a Python function which will print hello from TFD. This is just a boilerplate. We don't need it. So the first thing that we need to do is we need to, what we want in this package is to be able to list equations and then also show equations just like they show up in the book. So in the book, we have, um, yeah, so in the book we have, for example, this equation 5.12. And we want to show this equation as well as be able to use it. If we give it delta ti, it should give us q star. right? So then that's what we want to do. We want the ability